somewhere off a volcanic coastline, in water so deep that sunlight gives up long before it reaches the bottom. Something is talking. Not growling, not simply calling out, talking in patterns that repeat, shift, and respond to one another the way a real conversation does. For most of human history, we assumed the ocean was mostly silent, or at best filled with noise we would never be able to make sense of. That assumption just collapsed. A team of scientists, engineers, and machine learning researchers has spent the last several years building tools powerful enough to listen to one of the most intelligent animals on Earth in a way no human ever could on their own. And what they found inside all that noise wasn't just sound. It was structure. It was grammar. It was something that looks unsettlingly like a language. This is the story of how that happened, why it took artificial intelligence to crack it open, and why the implications might reach a lot further than the ocean floor. For most of human history, the ocean was something we crossed, fished, or feared, not something we listened to. Sailors told stories about strange songs rising up from beneath their ships, and for centuries those stories were dismissed as superstition, the kind of thing tired minds invent on long voyages. Whales themselves were seen mainly as resources: oil for lamps, bone for corsets and tools, meat for food. Their size impressed us. Their minds did not concern us. It would take a scientific accident, decades later, to change that. In the late 1960s and into the 1970s, researchers recording ambient ocean sound for entirely different reasons stumbled onto something strange. Humpback whales were not making random noise. They were producing structured sequences of sound that repeated, evolved, and lasted for extended stretches of time, sometimes going on for 20 minutes or more before looping back to earlier phrases. These recordings were eventually released to the public, and the reaction was enormous. People who had never thought twice about whales suddenly found themselves moved by the eerie, layered melodies rising from the deep. That release is widely credited with helping fuel the environmental movement that pulled several whale species back from the edge of extinction. But fascination is not the same as understanding. For the next several decades, the study of whale sound, a field known as bioacoustics, moved at a frustratingly slow pace. Researchers had hydrophones, tape recorders, and an enormous amount of patience, but not much else. They could tell that something complex was happening, but they had no reliable way to prove what those sounds meant, whether they carried anything resembling meaning at all, or whether they were closer to birdsong. Beautiful, but essentially reflexive. The tools simply weren't built for the scale of the problem. Understanding a communication system requires enormous amounts of data and the ability to detect subtle patterns across that data. And for most of the 20th century, neither of those things existed in a form scientists could use. The breakthrough, when it finally came, didn't originate in a marine biology lab. It came from someone who spent as much time thinking about space as he did about the sea. Marine biologist David Gruber had built a career studying unusual and often overlooked corners of ocean life, but he became fixated on a much larger question. If intelligent, non-human minds exist on our own planet, why had we never seriously tried to build a system for actually communicating with them? He found his answer in an unlikely place: the decades-long effort to detect signals from alien civilizations, a project most people know by its acronym, SETI. The logic behind SETI is straightforward. If intelligent life exists elsewhere in the universe, it might be broadcasting patterns we could detect and eventually decode, provided we built the right instruments and applied the right analytical methods. Gruber's insight was almost embarrassingly simple once you hear it. Why wait for a signal from another star system when there might already be a genuinely alien form of intelligence broadcasting from the ocean next door? Whales evolved in an environment completely unlike ours, developed brains several times larger than a human brain, and rely almost entirely on sound rather than sight to navigate their world and their relationships. In many ways, trying to understand a sperm whale's inner life is not so different from imagining what it might take to understand a mind that evolved on another planet entirely. That idea became the seed of an ambitious, almost audacious research effort aimed at doing something no one had managed before, not just recording animal sound, but building a genuine translation system for it. What made this project different from earlier attempts wasn't just ambition, it was who was in the room. Traditional whale research had almost always been the domain of marine biologists working largely on their own, spending years quietly observing individual animals and pods. This new effort brought marine biologists together with machine learning engineers, linguists, roboticists, and specialists in underwater acoustics, all pointed at a single shared target. At the center of the biological side of the work was a researcher who had spent more than a decade living alongside a single extended family of sperm whales near a small Caribbean island. He didn't just study these animals from a boat. With a notebook, he learned to recognize individuals, tracked relationships across generations, and understood their social structure in a way that took years of patient, close observation to build. That kind of intimate, long-term fieldwork became the foundation the entire project would eventually be built on top of. Without someone who already understood the whales as individuals and as a community, no amount of computing power would have known what to look for. Layered on top of that biological foundation was something whale researchers of earlier decades simply never had access to: modern machine learning, and specifically the kind of pattern recognition systems that had already transformed fields like image recognition and language translation for human languages. The idea was to take everything those systems had learned about finding structure in enormous, messy datasets and turn it loose on millions of hours of whale sound. Around 2019, the pieces started falling into place. The team realized they finally had the technology to build something that had never existed before: a large-scale underwater listening system capable of recording whale communication continuously, at a scale previous researchers could only have dreamed of. Not every coastline could support a project like this. The team needed a location where whales gathered reliably, where the water was deep enough close to shore to make deployment realistic, and where researchers already had a foothold. A small volcanic island in the eastern Caribbean turned out to check every box. Its underwater terrain drops off sharply, allowing deep-diving whales to come remarkably close to land. It also happened to host a stable, returning population of sperm whale families, including the very family that had already been studied for over a decade by the project's lead field biologist. With funding secured through a major science-focused grant initiative that provided tens of millions of dollars, the project launched formally in 2020. Its first major infrastructure goal was staggering in scope: an underwater listening network stretching across a wide swath of ocean, designed not just to capture sound, but to ears determined exactly who was making it, and in what social context. That distinction, knowing not just what was said, but who said it and why, was the missing piece that had stalled bioacoustics research for generations. The backbone of the project was a network of hydrophones, specialized underwater microphones, anchored across the seafloor in a coordinated grid. Unlike a single recorder dropped from a boat, this network operated continuously, day and night, capturing everything happening in the water around it. Because the devices were spread out in a deliberate pattern, researchers could do something no earlier team had managed: triangulate the exact location a sound came from, and, in many cases, identify precisely which whale had made it. That alone would have been a major advance. But the team pushed further, deploying small autonomous robotic devices designed to gently attach temporary, non-invasive sensor tags to individual whales. These tags recorded far more than sound. They tracked movement, diving depth, and even physiological signals like heart rate, while also capturing information about which other whales were nearby during a given exchange. In other words, the hydrophone network told researchers what was being said, while the tags told them the circumstances surrounding it, whether a whale was hunting, resting, traveling, or socializing with family when it made a particular sound. Combined, these two systems produced something the field of animal communication research had simply never had access to before. Not just a few hours or days of recordings, but a continuously growing archive containing hundreds of millions of individual vocalizations, each one tagged with rich contextual information about the animal that produced it. Earlier researchers had been trying to read a few scattered pages of a book. This team was building the entire library. Raw audio data, even an enormous amount of it, doesn't mean anything on its own. The real transformation happened when that ocean of recorded sound was converted into a form that machine learning systems could actually analyze. Visual representations of sound frequency over time, commonly known as spectrograms. Turning invisible acoustic signals into visual patterns allowed AI systems to do what they do best: scan enormous volumes of visual data for recurring structures that a human analyst would take a lifetime to notice, if they ever noticed them at all. The AI wasn't handed a rulebook about whale communication because no such rulebook existed. Instead, it was trained the way modern language models are trained on human text, by being exposed to a massive volume of examples and left to find statistical regularities on its own. Over time, the system began to notice which sound sequences tended to appear together, how those sequences shifted depending on context, and which subtle variations in timing or rhythm seemed to carry meaning. It picked up on distinctions in tempo, pacing, and tiny embellishments at the start or end of a sound sequence. Distinctions so fine that human ears simply cannot reliably detect them, but that machine learning systems, given enough data, could learn to recognize with startling consistency. What emerged from this analysis reshaped how the whole team understood sperm whale communication. These animals primarily talk using short bursts of clicks, known to researchers as codas. For decades, codas were treated as a relatively small, fixed set of signals, useful perhaps, but limited. The AI's analysis told a different story entirely. By examining variations in rhythm, tempo, and small ornamental clicks added to the beginning or end of a sequence, the system revealed something closer to a phonetic system. A set of building blocks that could be recombined in countless ways to produce an enormous range of distinct signals, not unlike how a relatively small set of sounds in human speech can be rearranged to build a nearly unlimited vocabulary. This alone was enough to overturn a long-standing assumption that complex, combinatorial communication systems were a uniquely human trait. But identifying the underlying structure was only the first half of the puzzle. Structure tells you a system has grammar. It doesn't tell you what anyone is actually saying. For a long time, the working assumption was that if whale communication meant anything at all, it was probably functional and fairly narrow: warnings, basic coordination during hunting, maybe simple distress calls. The patterns the AI surfaced told a much richer story. Rather than clustering tightly around survival tasks, variation in whale codas appeared far more strongly tied to social context: which family group was communicating, who the exchange was directed toward, and what kind of social interaction was taking place at the time. Researchers began to notice something that echoed human language in an eerie way: fine-grained timing changes within a coda, subtle speeding up or slowing down, similar to what musicians call rubato, appeared to shift meaning in ways that were consistent and predictable rather than random. A whale might use the same basic rhythmic word in different social situations, but stretch or compress the timing, or add a small extra flourish at the start or end, in a way that shifted its apparent meaning much the way tone of voice or emphasis shifts meaning in human speech. Even more striking, distinct whale family groups appeared to have their own recognizable dialects, consistent stylistic differences in how they produced otherwise similar codas. It became possible in many cases for the AI to identify which family was speaking purely from subtle patterns in their vocal style, the same way a trained ear might recognize a regional accent. This suggested that whale communication wasn't a single universal code shared identically by every sperm whale on Earth, but something closer to a living cultural system, passed down within family lines, subtly different from one group to the next, and shaped over generations. Put together, these findings pointed toward something far more sophisticated than anyone had confidently predicted: a communication system woven tightly into social identity, family bonds, and shared history, not just a set of practical signals, but something closer to a genuine social language. Understanding the shape of a language is one thing. Actually using it is something else entirely. And it's the next frontier this research is pushing toward. Having identified real structural patterns in whale communication, the team began cautiously exploring whether those patterns could be used not just to interpret whale sound, but to generate it, essentially building an early, extremely limited system capable of producing whale-like signals and observing how whales respond. This is not an attempt to teach whales a human language, nor to have humans speak whale fluently overnight. The early efforts are far more modest. Simple experiments using underwater speakers to play back specific, previously recorded coda sequences and see whether nearby whales respond in kind. In one especially notable moment in 2023, researchers played a specific coda through an underwater speaker, and a whale in the area responded with what appeared to be the same pattern back, an exchange that looked, for all practical purposes, like the opening of a conversation rather than a coincidence. It was a small moment. It also might be one of the most significant exchanges between two species in recorded history. This next phase of the work raises questions that go well beyond engineering. If researchers can produce convincing whale-like signals, what responsibility do they have to avoid disrupting the very social systems and dialects they're trying to understand? Introducing artificial signals into a wild population's communication system carries real risk of confusion or interference, and the scientists involved have been notably cautious about this, emphasizing that any future interaction needs to happen on the whale's own terms, respecting the integrity of their existing social and cultural structures, rather than imposing something foreign onto them. The implications of this research extend well past marine biology. For one, it offers something close to a working blueprint for one of humanity's oldest unanswered questions. How would we even recognize intelligent communication if we encountered it somewhere far stranger than our own planet? The methods developed here, using machine learning to find structure inside a massive, completely unfamiliar signal without any prior assumptions about grammar or vocabulary, are exactly the kind of tools that would be needed if humanity ever received a genuinely alien signal from deep space. In a very real sense, learning to listen to whales has doubled as a rehearsal for listening to something even further from human experience.